Hi everyone, welcome to this exciting topic. It's something that is up since a lot of time. We are going to talk about legacy virtualization and then the evolution of this topic that today is very trendy and how we can optimize that. So it will be something that will be very interesting, not just for technical people, but also for people that are involved in choosing the right product, in migrating effectively something. Everyone that was working previously on migrations from monolithics to microservices, architecture based, whatever we know about that. So let's start. Let's talk about the agenda and the chapters that we are going to follow. The most interactive section will be the demo. I am sure that everyone will be excited about that, but we will do a brief introduction on what is virtualization, the challenges that you can have and solve on traditional virtualization, how this approach of Kubevirt will solve for you a lot of problems putting everything inside Kubernetes. So the most important part is related to the adoption of Kubernetes as the scheduler for this kind of orchestrations, the key benefits of migration, the demo. Everyone will like the demo a lot. Example use cases, because I put just two typical use cases that you can have in companies that are deciding to move out from legacy virtualization, but you can think about that also for the providers, people that are working on the cloud right now and they want to create something more stable. And then the conclusion and question and answers. This was for the live presentation. For whatever question and answer, there is a comment section that will be very interesting to look together at. So this is me, Fabrizio Sgura. I'm the chief engineer at Veritas Automata. I'm a QB astronaut with the jacket. I received my jacket time ago, and I'm very excited to be talking about my expertise on Kubernetes. This effectively led me to create this demo, this presentation, and the fact that on Kubevirt there are not that much tutorials working effectively as expected. You have to follow runbooks, but they will generally have a lot of problems. So let's enjoy together life in all of its aspects, and let's start the journey inside this legacy virtualization introduction. We talk about something that is not from yesterday. I mentioned specifically the 60s and how IBM developed at that time a sort of mainframe based virtualization. So, the ability to do partitioning of the resources to create processes that were not just like the known chroot environment in the 60s. We are not talking about that really, but isolation, what we do together and on the kernel for the namespace isolation, that kind of thing that today is effective. At that time, there was a big mainframe. The way to use all of these resources were just a chair with a console for the operator. So it was really hard to think about optimizing this kind of available hardware resources. But they were just at that time thinking about this problem solving challenge, and they started with the control program. Then, evolving from that concept in the 90s, and especially in 2000 and later, many organizations were talking about virtualization. One in particular was VMware, that was creating some kind of executables. I remember that I installed the first VMware workstation in Windows, and it was Windows 95. So we are talking about 30 years of existence from VMware, the approach of virtualization. There were no hypervisor at that time, so we were just using an executable very similar to the today's VirtualBox or VMware workstation approach. And they started this trendy journey that um, we traveled together until we reached the current days, where VMware is still legacy virtualization, the old approach. You have to, on bare metal, run their own set of tools. You can compare that to VirtualBox, but when you think about the format of the disks that we are using, the VMDK, that is the typical standard format of VMware, is still an adopted worldwide standard for that kind of thing. Here I do an evolution of how these virtualization technologies we are talking about, so leaving out the 60s and IBM, let's start from 1998 when VMware created this first set of executable. Then they added the hypervisor on top of that. Physical hardware was involved, so you could have been having a dedicated server to run your specific virtual machines on top of that manager, an operating system dedicated to fulfill your requirements for whatever related to the virtualization, and still coupled to the architecture of the operating system and computer CPU that you were using at that time. Then we moved to the idea of another approach, Xen. I will not go too much digging in the historical things related to Xen, but think that is a natural transition that is in the middle and was widely adopted by EC2 virtualization in AWS. So if you are experienced and you worked in AWS in 2013, 12, or 15 also, depending those years, you would probably remember that looking at the console of the EC2 instances that you were using, you would have been seeing a reference to this Xen virtualization. But Xen was really limiting a lot of things. So gradually, everyone moved to this specific standards that is very important for us, that was developed and consistently evolved since 2006, that is KVM, the kernel-based virtual machine. Naturally, it's for Linux, so you have to run a Linux, whatever, server, workstation, a system. In my case here, I'm running a Linux 64-bit x86 architecture, and we will see that thanks to KVM, I will be able to virtualize a lot of operating system, and I can also work on different architecture like ARM64, PPC64, and whatever is supported by the QEMU and KVM integrations and drivers. Up to this, we move to the current times where Kubernetes is already a standard scheduler, the most widely diffused in the world at the moment, most widely adopted. And on top of that, in 2018, they started to create the abstraction layer to run QEMU KVM virtual machines as pods. So all the things that, if you know Kubernetes, are related to the ability of scheduling resources partitioned by pods, deployments, and exposing services, and whatever more you can imagine on top of the Kubernetes cluster, then think that that is possible also for virtual machines thanks to Kubevirt. Let's see how a deployment or something like a bundle that is mixing the two workloads that we are talking about is conformed. Here I put the legacy virtualization with the OpenStack logo, not because OpenStack is legacy, it's still very trendy, very widely adopted, but it is especially for real virtualization, not nested virtualization, not mixed workloads. It is for running the virtual machines as they are. So it's a silhouette infrastructure. Then we have the cloud native option where we have Kubernetes, the ability to run on top of that deployments, servers, operators, serverless applications with Knative of the APR approaches. So a lot of things that you can do on top of this big scheduler that is facilitating you a lot of tools for solving the service discovery problem, the network problem, whatever we will see in deep soon, and putting all together, moving out from the concept of one siloed, bare metal only infrastructure and another one running on the cloud that is consolidated to this Kubevirt hexagon on the right, that is Kubernetes, virtual machines, pods, and whatever more, and all the resources you can schedule on top of Kubernetes. Pain points of legacy systems are typically what we have to look at if we are, in example, commercial people oriented to the costs, the optimization, the productivity in general. So a limited automation and high licensing costs on virtual machines, it's quite clear you have to buy server licenses, a lot of products like the VMware bundle, vSphere, Fusion, a lot of integrations, and that will cost a lot, and it will also limit your automation because if a new product is out there available, you will not be able to initially integrate that in the bundle until the provider decides to support that for you. Then the incompatibility with Kubernetes native workloads is a trendy topic because if you think that many people are really putting their effort to develop on top of Kubernetes a lot of solutions running their pods, their containers, their serverless applications. The integration with a runtime that is on top of a virtual machine running at your home, in example, or in your own data center, is not directly something that you can integrate. You will have to bother about HA proxy, ingress controllers, a lot of load balancing things to do the endpoints available. And that will be an incompatibility that, in terms of productivity, will affect your whole deployment for the resources and also teams management. The people will get affected, but by that kind of resources that needs to be coupled in a creative way instead of having it ready to go. And then the operational overhead and reduced agility, especially because optimizing the resources is something that is limited to the power of the virtualization tool that you are using, and not, in example, by resource partitioning like you can do in Kubernetes, CPU, memory, storage, a lot of I/O and hardware-dependent activities or virtual hardware-dependent activities too that you can manage easily in this kind of Kubernetes versus the approach that is legacy virtualization. Some challenges here, they are still mentioned because it's really important to consider that time is money. The challenges lead to loss of time, to inability to solve problems consistently. So if you don't have a ready-to-go solution, you will need to spend time, people's effort, a lot of additional resources that will be creating a lot of challenges and costs. So lack of Kubernetes integration, we already talked about that. This is something that will affect the scaling ability that you can have, sorry, from this kind of dynamic cloud native architectures. Probably I'm not virtualizing my voice, so I'm having that specific problem, but I'm working on that. I'm putting Kubevirt in my body to solve the problem. So let's go for the hybrid workload management and another challenge that is related to operational nightmare and the DevOps activities of the teams that needs to work on the specific workloads of your applications and the hardware that is running to support the whole ecosystem. Then the resource allocation inefficiencies, we talked about the ability of knowing how many CPUs core you can use and how do you want to use them, and the memory, the disk size, the optimization of these fragments, that when you have a lot of deployments will be very hard to do in a matter of inventory or something that is really optimized by percentages. If something is doing that for you, like Kubernetes and the scheduling abilities, then it will be removing the siloed environments that we looked at in OpenStack and legacy virtualizations. And performance limitations is also related to the fact that if you have a cluster with a lot of CPUs, in example, and the applications are running just on top of a node or a virtual machine, you are not able to consolidate all of your cooperative resources, and you will be affected in terms of challenges and performance from that specific perspective. This is the representation, a graphical one, of how the hybrid workload gap versus the real ability to manage all of your resources. So when you have a centralized system that is scheduling the activities for you, but is fragmented, like in the case that you see each different virtual machine running as a separate entity, you have management fragmentation, you have a problem to do changes, everything related to GitOps activities, the current technologies that are really getting better in terms of cloud native administration. But also, if you are running on bare metal, they are still valid, like the GitOps pattern. It will really be complicated. You will need to wait for a specific Terraform driver, like the libvirt one, to be produced and maintained. It will not be something that you manage from your own laptop or your own console, just using the kubectl command, in example. And this is the typical representation of the case study we are talking about. So this fragmented bundle of resources, the prevent on challenges like innovation and migration. I talked at the beginning about the ability to have migration strategies, not just from monolithic to microservices like it was trendy in the past years, but also from an architecture to another. So you are running an example of something on the Mac, and you want to port that specifically on another architecture with short amount of time, or ARM64, you are running something on your Raspberry Pi and you want to emulate that on top of a Kubernetes big ecosystem, that is where you will be interfacing these kind of things. And with all of these parts that we talked about, the scaling challenges, if you think about not having Kubernetes, are bigger enough to consider that we need something different. So now, what is Kubevirt? For our case, it's first of all the ability of extend the Kubernetes API to manage the virtual machines. What is an operator? We already talked about that. You can rely to other videos that we have in other channels when we were presenting about operators. But basically, the main concept is that we extend the Kubernetes API. So we have the ability of creating additional functions, additional processes based on top of the reconciler of the event-driven Kubernetes stack, and we can react to the new custom resource definition that we can create for each of the resources we are going to use. And if you think that a custom resource definition could describe your virtual machine, in example, and you can have a reconciler taking decisions on top of that, like running the QEMU command line to create a container with a virtual machine inside of that and a persistent volume claim, then you think about extending the Kubernetes API, not just as a fantasy, but as a matter of fact. And combining this stability of the VMware previous approach, legacy virtualization, whatever you can run on VirtualBox, also with the OVA format, or whatever you have from the previous approach, to convert to Kubernetes automation and integration. This will also be a benefit because we unify completely the management. So we don't have to own the team that is dedicated to run virtual machines on top of a data center that is running VMware, then another team running on the cloud instances on AWS, in example, or Azure, and another one specialized on Kubernetes. We just put this bundle all together. We search for people that are familiar with the three concepts, or if we want to train people to learn about that, we just have a single point to work on, that is Kubernetes. And this, obviously, for companies, for people that are looking at pockets, it's cost savings. Less fragmentation, more optimization, scheduling of the resources, everything that is not just that technical, because it's not that pod that we know is running the emulation for the kernel, virtualization, and whatever. But if you are really looking just at the pocket, it saves you money because it means that you have less fragmentation on the resources that you are having to bundle for creating a project, maintaining it, also taking care of migration. And this evolution, this evolving, elapsing um, animation that we have here is exactly how you start when you start from on premise and you start having the gradual improvements, adding the Kubernetes, running VMware on top of that, and having full control on a console that will facilitate all the job for you. Kubernetes wins over traditional virtualization system, and this has been clear in the previous slides because of cost, because of resource scheduling, availability, but it also has the open source community and flexibility. And think that when you have a need to create a new tool and you are relying on a community that is spread worldwide, you don't need to find a way to create a lot of design meetings and similar. Probably the solution is out there, and just opening an issue on a GitHub repository where a specific product is maintained will solve 90% of things for you. You just have to bother about the integration. So the open source flexibility is something that you have to keep in mind, because Kubernetes and the community built around the scheduler, it's really big, constantly evolving. It has a lot of applications available in the landscape, and the quality is ensured by the community itself. So there are special interest groups, the Kubernetes Enhancement Program, a lot of resources that are driven by experts for you. Seamless workload integration is really important if we think about what we talked about earlier for the part related to the consolidation of the teams, the hardware. Why not thinking about that? You could decide to move out from the cloud. Today, it's very trendy to start thinking about the opposite of 10 years ago. Everyone was going to the cloud because it was considered a better choice. You didn't have to bother about maintaining a server up, um, talking about memory replacements, hardware, CPU, and whatever. It was just thinking about your applications. But the real point is that it never worked that way. You had to hire specific experts for the cloud. So basically, whatever you were doing on bare metal is translated probably to more costs, because the cloud will bill you for more costs. And if you think about servers and power, that are the main resources with the provider and the internet connection to run your own server, probably doing a couple of math on top of the money that you are spending for that, in many cases would tend to be analyzed as something that you can really come back to the bare metal, and this seamless workload integration will be foundation for moving your resources from the cloud to the local hybrid clouds, whatever is required for that. Or if you want to virtualize your own resources by using Kubevirt on top of Kubernetes, you will create a local cluster of nodes. And we will see in the demo that is not that hard to do. You really need some minutes if you are already experts on the Kubernetes side. Unified interface, I already talked about that, is the ability of having people just focused on what they know. So they will also have a challenge reduced on top of an example problem that they could have in production, uh, something that could happen as an exception. They will know that most of the exceptions are around the Kubernetes ecosystem, and they don't have to bother about that kernel driver that is running QEMU, KVM, all the components, because the setup is already consolidated. And Kubernetes, the operator, and the handlers on top of each cluster node, they will manage that for you. So it's just like having a big hypervisor, but without the need to have a specific console to learn about. It's just Kubernetes. And this, again, will lead to cost savings. A lot of money that you will save because of this consolidation. If we look at these 4 points now, the future proofing for CI CD practices, think that you have all your CI CD real environment and testing for end to end integrations and similar. Everything is available virtually. So the production environment can be reproduced 100% real, like the offline one that can run. It can be the QA testing environment or the UAT. You can have several stages. If you add Canary deployments, you can imagine what more you can do on improving your CI/CD. Other point to save money: less testing, more focused tests, more bug catching during the development process. I would not go over because it's quite clear that for this adoption, you will be having a benefit also in your supply chain use case. Then we have the real world success that is practically given by the total cost of ownership for the infrastructure that is consistently reduced because of the optimization and what we talked earlier. But it's really something that companies that adopted these standards are already a case success, and they are available on many newsletters to give the witnessing point for what they were experiencing from moving out from for one solution from another one, the new approach on Kubernetes. Kubevirt as a solution, it's not the only one, there are others. So you can think that Kubevirt is the base for moving the workloads to Kubernetes. It's the base that many other enterprise products are using as a base. I will just mention one because there are many, but one is Harvester by SUSE, and it's using Kubevirt with the other bundle of resources that is available in Rancher. So there is also a case for OpenShift and other things. But basically, Kubevirt is also a standard for those kind of enterprise deployments and solutions, which means that you have a common core, this case study of Kubevirt to introduce in your team, and nothing more than that for having the people trained. This means that you have enhanced scalability, flexibility. If something new comes out, generally the upgrades on Kubernetes are one Helm upgrade, or if you are using a sort of control like FluxCD or Argo, is just changing a variable for having that on the development cluster. And then if everything succeeds, you just go to production. It's really easy to integrate these kind of workflows in an environment that is already supporting the scheduling ability of Kubernetes. Here we have a chart that will describe how on top of a Kubernetes cluster, on the left side, with the agents, the master with the controller and the API, and Kubevirt running on top of that, you can have applications and virtual machines, the pod with the virtual machine inside. It's a logical inside because it's just the disk of the source machine attached to the pod, the persistent volume imported in Kubernetes. For the second part, we are talking about mixed. So I'm running a VM as a pod, but I also have other containers. And this could be the typical use case of the Ingress Nginx controller to expose the public endpoints that is your web server endpoints in IIS, in example. I'm talking about IIS, it's Windows. We can virtualize Windows too. So why not considering that we will see in the demo, we are also running Windows Server. And there are consequences for costs and company migrations on that. I don't have to add Windows containers. I don't have to run on Azure. I don't have to run my Windows Server. I just have to run Kubevirt. And the third part is the typical application on top of Kubernetes with pods in containers and your application that is running as a cloud native workload. On the right side, this consolidation is more for the upper part in pink. That is what Kubernetes and Kubevirt together will give us. The ability of having these three hexagons describing mixed workloads that we bundle together in our ecosystem for whatever. And CI/CD, GitOps, tools for managing all of these are included in this consideration. Real world impact here, I think that I was trying to describe that Kubernetes is wherever. We just have to look at how many certified people on Kubernetes are worldwide present. It's really better than a unique language. It's like music. Everyone will listen to it. For the moment, Kubernetes is the wide adopted scheduler. So when legacy applications can coexist with microservices, serverless applications, so just functions running inside Kubernetes with whatever Knative or the APR approach, you can really have a benefit that is extensible. And the hybrid cloud portability, I mentioned that. We will see that in detail. To run the whole workload, you will have to buy bare metal instances, in example. If you do that on the AWS provider, you will have a consistent cost because they are offering solutions that are very big and scalable, but you really need small nodes. So I would not say run in your own data center. There are physical bare metal providers, like one name is OVH Cloud, another is Rackspace, very known on the market. There are many. They are arising like mushrooms right now. That kind of ability for deploying on bare metal from your home with the IPMI console and install your own operating system, it's hybrid cloud portability. You can have your applications running on top of AWS right now. EKS, in example, could be an option. And then you create the other bare metal, nested virtualization, Kubevirt approach, not running in your own data center, so still not having hardware costs, but renting a server for 1 month from these providers and pair the resources together. This will be not just the ability to be portable, but the improvement of performance, because the more a resource is available, the more you know how to extend that, the better will be for reliability. Think when content delivery networks were adopted on top of the clouds and we were having regions worldwide for deploying that. You still have regions if you adopt the mixed bare metal option from Rackspace or OVH Cloud because they have regions for you. So all the performance that could be affecting you on the network side, IO side, and many other things like those, you can solve because of this worldwide constant impacting part. Finally, the demo. So we have time to go for a video that is embedded in the demo where I will describe the Terraform stack that I created. We will see how the cluster is composed. That will be a live session, how we deploy the pods and components. Rancher console, I've been using Rancher because I've been using also the RKE2 5 nodes cluster locally. Longhorn storage class to ensure that for our virtual machines, the disks are persisted, replicated, and also snapshotable. Then how we control everything from Kubevirt. There are really a lot of subcommands in the kubectl extension, and in the virtualctl tool, we will not be able to go one by one. We will just use a couple, but it's full of options. Then a new concept that is the CDI, the container data importer. Like in Kubernetes, we have a CNI, a CSI, and whatever more. We also have a new standard that is maintained by the Kubernetes Enhancement Program that is CDI, so Container Data Importer. That will mean that we have a way manifested and documented to do this import of the disks of the virtual machines. Then how we convert disks from VMDK, OVA, whatever, on the command line with QEMU image convert to quick code 2, that is the format used by KVM and QEMU and Kubevirt 2. I included Metal Load Balancer to show you how you can expose services and ports running specific services on top of virtual machines with a simple manifest and the operations. So here, I will go to the demo just very briefly, the video first. Here in the video, I have my terminal in the folder that is available on GitHub with the libvirt stack that I created for creating this cluster of RKE2. You see that here I'm running the Terraform init. When we will run the Terraform init, we will have all the modules, libvirt provider, and whatever more is related to the deployment available in our machine. With the validate, I just checked that I didn't introduce errors. Here I have the plan. You see that I'm creating a lot of resources. Generally, they are network master nodes. I haven't take that much to create a bundle of effective variable TF file for describing how these arguments and parameters are the description of this deployment. I'm just applying the plan now, and you will see here on the right side that this is the libvirt manager. 5 nodes will appear running the cluster. So you see now all the 5 nodes of the RKE2 cluster, 3 masters and 2 agents, are up and running. They are just performing the initial activity on top of all of these resources that are available there. I already have the console. Here you see that is just a login interface for this node that I'm looking at. I am showing you also the screen zoomed for you to recognize that is a Ubuntu LTS 2022, and it's a cloud image. Here there are the resources that I assigned to the machine. So you will see here it's a KVM hypervisor running thanks to my kernel. It is having a limited amount of CPU, 4 cores of 24. The topology is a host pass-through. So for this case, the architecture is the same as my computer. I'm running 16 gigabytes of RAM for each node. And here I'm just using the virt.io driver for the disk, so I'm not installing special controllers. The network is already describing how we can have a deep IP address management by libvirt. Think that I already solved one problem. I don't have to bother about VLANs, configurations for the network, and whatever more thing that could be affecting your team when they have to do a design on the infrastructure. And we are still not on Kubernetes. So with libvirt and the ability of creating something that you could run on a bare metal provider, running the IPMI console and installing exactly these nodes, you will have the same situation with the same resources, the IP assignment. I'm using a NAT network here. You can also run a bridge one, so you can have network isolation. It's a lot of features that you can really manage without having to be designing that on a table with all the team um, running an architecture meeting for doing the network and infrastructure. It's just run it and use it. Here I'm connecting to a node that is the master one. I'm demonstrating how I entered with the SSH console to a local IP address of my network. So everything is seamlessly integrated on my network. We can move a little bit faster because here what I'm doing is that I'm taking the kubeconfig file for RKE2 to my machine to show that I can also access from my machine to the whole cluster resources. And here again, I'm just copying it out. I will speed up because this part is relative. I just have to change the server endpoints to reflect that IP address that in my case is static for the masters. And finally, once I have that specific file, I can get the nodes of the cluster. We will see that I will do that also for the rest of things. If we scroll more, I'm just doing another scenario landscape of a virtual machine that I previously created on libvirt. So think that I use this Ubuntu 24. I created the Ubuntu 24, and imagine I use the same disk that I will later import in Kubevirt to have exactly this virtual machine running on top of the Kubernetes cluster. Speeding up, this is the virtual machine that is available. I created a file on top of this virtual machine that I was accepting by the SPICE interface. And that file we will see that is still available in the current up and running virtual machine. So think about the video that really following up with the video is something that will be available in the presentation, so you can go ahead. I want to give you a practical example of, before exiting the slides, and giving you the practical example of how these nodes are done, the resources that are here. So I have still the 5 Kubernetes cluster nodes. They are up and running. They are by get nodes visible here. They can be enumerated by the pods. So you see that here in get pods, I have a lot of components that are from the Calico, CNI, the fleet installation and rancher that is done by a next step available on the Terraform stack, because I decided to include that console as an easy to manage step for the cluster. Here is the CDI. I was talking about that container data importer, and here it's the upload proxy that we will see it's exposed to import disks of the virtual machine. These other components are related to the certificate manager in Kubernetes, the rest of the kube system components. Here is the Kubevirt deployment with the operator, the daemon set with the handlers for each node, a controller, and the API that is giving me the ability to control my resources created and managed by the controller and the operator. Finally, an approach for storage using Longhorn that is giving me the ability of having a very, very solid storage solution and snapshots and persistence for the data, including backup, disaster recovery, and similar, and metal load balancer to expose the service ports we will see soon. Then I included also a monitoring, but this is another chapter. So a question that I had was, how can I monitor virtual machine? You just run node exporters by Prometheus, and you will have all the metrics that are available for the virtual machines, including CPU usage, memory, applications profiling, and similar. And then with Loki, you can also have your um, logs from the virtual machines. You will not lose what you had on the previous data centers approach with the legacy virtualization. And at the end here, I have two namespaces. You see, I have the Linux namespace, the Windows namespace, and I'm having up and running three virtual machines, one Windows, one Ubuntu, one R64 Debian that is still not working because of the bootloader, but it's there, available. These virtual machines we see here that they are available as a resource. Get VM will give me the status of the virtual machine, how is the age of each virtual machine created, and the virtual machine instance will give me the IP that is assigned. It's a name to IP, so I don't have to bother about that. We will see that Windows Active Directory can work without having a static IP assignment because everything is assigned with the Kubernetes conventional service and resource mapping. So service discovery is completely solved. Here I see how I expose the services via the metal load balancer on a local IP address of my current network. I have in this Ubuntu uh, a nested Kubernetes, the SSH server. For Windows, I have IIS and the RDP console, and they are already working. We will see at least the IIS. Here I have the disk that I used to convert the Windows VMware created virtual machine. It was initially created in VMware, then translated and tested on libvirt here. And the disk QuickCo1 produced that here we see the source is the VMDK of the Windows Server and all the slice. In the previous folder here, I have, no, not here, but in this folder. So here, I have also the QuickCo converted disk that I imported. Here, I'm showing you how I created this QuickCo2 importable disk for the Ubuntu. And we will see how, in this case, I access, start and stop a virtual machine with the virtctl command. This is for the Ubuntu, so let's terminate it and let's run it again just to access the physical virtual machine. This is a pod running inside Kubernetes, but it's also a virtual machine that you can access the conventional way using this SPICE interface from QEMU. So it's a default. And here, as I was telling you, I installed a nested Kubernetes K3S node that you can reach also with the service exposed from your local machine. Just a brief look at Rancher. Here, when you have Rancher installed, you will have the console that will allow you to access the local cluster and see all the resources that are running. Here, I'm using a lot of CPU. You can imagine that all of this deployment is done locally on my machine. Here are the real resources, 24 cores. Almost everyone is used consistently. 86.2 gigabytes of RAM out of 128. So you need resources to do this test locally, but you can also spin up just a one node cluster. It will work the same way with less power on virtual machines. The workloads is what I showed you earlier, all the pods that we saw. And the ability of having Longhorn embedded in this console is self-explanatory. We have control on our storage. This is a dashboard, but if we go to the nodes of the cluster, here they are the 5 nodes with the resources that I'm having available for each node, the persistent volumes and space that I can use to create them. Here we have the disk of the Windows machine, 43 gigabytes, and the disk of the Ubuntu machine. This is for the other machine that is the ARM64 emulated machine. If we click on the persistent volumes, you see that you have RAID 5 here. So it's full replica, and or let's say that these are really a mirror on top of 3 disks. So if you lose 2, it will still work. It's not really a RAID 5. You can take snapshots. You can create jobs for backing up, snapshotting the file systems, and you will just do the backup of your virtual machine, taking a snapshot from here. Like I said earlier, I was exposing the Internet Information Services web server from the Windows machine. It's here, still working and answering, and the Windows machine is available again as a PSpice console. I haven't purchased the license, so I have a lot of things, but this is a Windows 2022 server. If we run the NSL lookup from here to the endpoint that we are seeing in the other node, we will just communicate via the service endpoint that Kubernetes is giving us as an option. So you see that here, again, running that VNC connection for the VirtCTL VNC. It's not really VNC. This is for Windows. I will terminate and run it back. So here you see that I'm just accessing to that. I can do whatever activity I want, like a normal server. I can install services. I can use the RDP to manage it. I can watch at the IIS on my machine so that it is exposed as a service. And this is more or less a big advantage that we can have from the Kubevirt integration and deployment. Coming back to our slides, very briefly, we have 3 minutes to consider the rest of the use cases. So think about a company that was having financial services running on top of a monolithic. They had to do migration, modernization. They wanted to migrate a lot of workloads from VMware or whatever other legacy virtualization system. And they wanted to cut costs on licensing, reducing the VMware part, locking part for the whole ecosystem. They wanted to adopt a solution that was already valid option for continuous integration and delivery with the Kubernetes availability tools for that. And they succeeded in doing that, improving all of these aspects, moving their monolithic approach translated to a lot of translation of these virtual machines on top of Kubernetes, and this is a success case. And then we have a use case on a company that was having hybrid cloud. So what I was mentioning earlier, more or less, but here with the 3 main points that were the painful aspect and also the benefit of moving out from that. The on-prem cloud management, it was always something that required special abilities from the team. The need for having a consolidated strategy across the hybrid and public clouds, moving out from that and adding a common layer that improved performance, reliability, cost savings for the team management, less people involved in many fragmented activities, cost savings, and operational efficiency. So the future, at least for me, is cloud native. I think that's a common trend because everyone is thinking that legacy virtualization is coming to an end. We need to find a way to do a consolidation. It's already out there. It's Kubernetes with Kubevirt. We just need to embrace it, adopt it, and this is really our opportunity to become better in what we do in IT. Thank you, everyone. It was a nice landscape view and scenario for the future and, for me, current adoption of the legacy virtualization breaking point and move out, embracing these cloud native workloads and technology, feel free to ask whatever you want. Remember that in this presentation, you will also find the reference to the GitHub repository where we have all the material related to the demo. This is me. Goodbye. Thank you for being here.